All right. So recording. We'll see how this goes. I, 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 I think I'm. Who cares? Uh, yes, I've noticed when doing basically these what are called velocity-dependent force problems that sometimes I've had to use u-substitution, and even sometimes in some of the other calculus, I've had to use u-substitution. So that's kind of like why I'm doing this or teaching this. And essentially, u-substitution is where you see an integral and you go like, oh God, I have no idea how to do that, right? And you go, and you go, wait a minute. Because U substitution assumes chain rule. In fact, we used U when we were doing chain rule as well. Um, and so basically you go, oh, I can see a function within a function. I'm going to call that U. And then I'm going to, basically you take the derivative of it. This is how you do U substitution solving. And then you plug in everything in terms of U. And then it makes for a much easier integral. You do the integral and then you plug everything back. That's U substitution. So here we go. Here's the first one. Integral of the square root of x cubed plus 5, and then multiply that by 3x squared dx. And I look at this integral and I go, holy crap, I have no idea how to do this. Right? And so you go, oh, wait a minute, U substitution, because I can see a function within a function. Where do you see a function within a function? Yeah, x cubed plus 5. So that's going to be my u, x cubed plus 5. So that's the first step, is identify a u and then write it in there. And then you take the derivative of u with respect to, whatever this variable is, in this case dx, so it's du dx. So what's the derivative of u with respect to x here?
3x squared.
Yeah, and then the 5 drops out. It's a constant, right? The next step is to isolate dx. Again, if this is on YouTube and mathematicians want to yell at me, sorry, this is what we do in physics. So du over 3x squared equals dx. And now I'm going to just replace everything in terms of all of those. So this is the square root of u, which I'm going to rewrite as u to the 1/2 power. And then instead of dx, I'm going to replace it with, so I got 3x squared, and I'm replacing dx with du over 3x squared. And the 3x squared cancels out. That's a much easier integral to do, right? So this then becomes the integral of u to the 1/2 power du. I can do this now. I just add 1 to the power. So 1/2 plus 2 over 2 is going to be the integral. No, I'm doing the integral. So integral of 3/2, but then I multiply it by the reciprocal. And then I add a plus c, and that's my answer, except I want to put the u back in. So it's going to be 2/3 x cubed plus 5, 3 over 2 plus c. Do another one. Sine of the natural log of x is equal to dx over x. Let's just put the over x here. Okay, so again, we already know that these are u substitution, but if you saw something like that, you probably go, oh God, I don't know how to do this integral. But then you go, wait, u substitution. What could I make my u here? Where's the function within the function? Natural log of x. Next step, take the derivative of u with respect to x. What's the derivative of the natural log of x? 1 over x, yes. That's the tricky one, right? So the relationship between a transcendental and a polynomial function is the natural log of x and 1 over x. Again, next step is isolate x. So it's going to be x du is equal to dx. And I will replace that. Now this becomes integral of sine of u. and then over x, and then we got x du replacing dx. You can see the x cancels out. Much easier integral. Do we recall the integral of sine of u? Negative cosine of, u, but u is the natural log of x, so I can plug that back in, plus c. All right. And then this one here, so x e to the negative x squared dx. If you notice, right, already, if I took the derivative of this, it's negative 2x, right? And that's the same power, right? That's also a thing you can recognize if you can find a u-substitution. If you can recognize that, oh, the function within a function has its own derivative on the outside, right? Then, oh, that's probably a u-substitution thing. So truthfully, when you're doing math, you might look at something and go, oh, maybe this is u-substitution, and then you go, oh wait, no, it wasn't. Never mind. And you can try like other methods, but yeah, okay. So function within a function. What do we want to use here? Negative x squared. Next step, take the derivative with respect to x. Negative 2x. Isolate x. I got that. I'm going to plug it in there. Then this becomes the integral of x e to the u. And then instead of dx, we're going to have du over negative 2x. X cancels here, which is good because now I got everything in terms of u. So I got negative 1/2 integral e to the u du. This is my favorite integral. What's the integral of e to the u? E to the u. So good. So it's negative x squared and then plus c. And you're done. And you can always check these like usual, right? Because you did the antiderivative, you did the integral, so you can just take the derivative, and if you get the old equation back, likely that's correct. Questions here so far are going to start doing separation of variables. All right. So separation of variables is we've seen differential equations already where, right, if they fit this general form, that, what you fit it in this form, and then whatever is in front of your delta x, that's your omega. So that's like your your omega for the general solution, that the amplitude times cosine of omega times t. And so for the omega, that's there. Then you just need to find the amplitude, and boom, you've got the solution. You got a position as a function of time. Yeah.
If we see like a bunch of constants in front of the x, is that equal to
omega squared? Yeah. I usually say like, oh, now you know your omega. What I mean is now you know your omega squared because you just need to take the square root of that to get it. Yeah, exactly. Like we saw with the Earth going right up and down. There's just a bunch of constants in there. Okay, that's what omega is all those constants. And again, a differential equation is where a variable is equal to its own derivative, right? And here's a variable equal to its own second derivative. We call that a second order differential equation. But these are called first order differential equations because you have a variable, you got a variable, and the variable is equal to its own derivative. In this case, though, the first derivative, hence why it's called a first order differential equation. Just like with degrees, right? We know something with a degree of 3, meaning cubed is the highest power. If it's a degree of 2, squared is the highest. It's a quadratic, et cetera, et cetera. Okay. So there's many ways to solve differential equations. In fact, some ways of solving a differential equation is you just go like, I'm just going to guess the answer and check to see if it's correct. We are not going to deal with any of those differential equations. They will all be solvable. So this one's solvable, and it's solvable by this method it's called separation of variables. And basically it goes like this. How many variables do I have in this equation? 2. You got x and y, right? This is just the derivative of y with respect to x. But, so you could say, this is also a variable, but we're just going to say 2 because that's just the derivative part. And what you do is you separate them. When separating, addition and subtraction, rarely used. You separate by multiplying or dividing. This is just kind of my experience. It's every time I think like, I could just add this over. It never works. Then, so you can see here, and you're trying to get all the y's on one side and all the x's on the other side. So I can multiply the dx over here and divide the y over to the other side. Again, math people, sorry. So I'm going to have 1 over y dy equals 4 e to the x dx. So any questions on how I separated that? Okay. The next step. So I've separated the variables. Check. Next step. Integrate both sides. So, but if you notice, each integral is different. This one is with respect to y. This one's with respect to x now. So, here's the tricky one. 1 over y. What's the integral of 1 over y? Natural log of y. Truthfully, it's the absolute values. I have yet to deal with that, so I just throw them out. We're going to be okay. And then it's also plus c. Turning it, yeah. I'll just take it, just so you don't have to.
Well, it's not done, but.
Oh, okay, sure, yeah. Okay. So then I do that, and then I'm going to integrate the next side. 4 is a constant. I don't need to worry about it. What's the integral of e to the x with respect to x? E to the x. And then we got plus c. Well, they're different c's, so I could call one c1, c2. Last step is isolate for y, basically your dependent variable. We'll see what this looks like with physics in a bit. So to do that, I'm going to subtract both sides by c1. So this will be minus c1, and this goes away. So I got some constant c2 minus another constant c1. What's that going to give me? Another constant. You could call it c3. But we tend to just go like, you know what? This is just a constant minus a constant. It's going to equal a constant. Let's just call it c. And so I tend to call this, I've recently started calling it this. I like it. It's the Uber constant, and it absorbs all other constants, okay? Because you can always just, you get a constant, you just subtract it or add it by a constant or multiply it by a constant, and you're just going to get another constant. So it just absorbs all the constants. Like, yeah, some of math, not that math is getting thrown out of the way, but it's like, it's kind of a convention. It's a funny convention, though. So you get e to the x plus c. And then lastly, I'm going to do the, so this is the natural log of y. So I'm going to raise everything to e to undo that natural log. Whoa, wait. Oh, wow. Okay, e to the x, Yikes. Holy crap. Did I make a mistake? I don't remember doing that. Natural log? No, e to the x. Okay, all right. I did. Thank you. So we got 4 e to the x plus c. Okay, and then this will give you y, because again, the e here cancels out with the natural log. This will give you e to the 4 e to the x plus c. But then, so this is all well and good, and honestly, this is a solution. You know, sometimes you need to find out what C is, right, or something like that. Like this is totally fine. However, often we can go, oh wait, e to the something plus c. That's the same thing as saying 4 e to the x times e to the c, right? That's a property of exponentials, and so we can use that. Well, we got e, which is a number, to the power of a constant. So that's just going to be another constant. So uber C strikes again, and it all absorbs into the same C. So my final answer here would just be y C e to the 4 e to the x. You want me to? Are you done?
Yeah.
Congrats! Oh, okay. All right. Got it. T.
Is there ever a situation where we can't just combine the constants and like turn C1 to
I'll put my one.
the E to the C to just.
No, that is what we do. Yeah.
So, is there no like circumstances where like we can't do that?
You know what? Yes, it does show up. Or not that we can't do it. Like we can always do it, but like to solve a certain problem, you go like, oh dang, I need that C that was back there, you know? And so you go like, okay, so I'm gonna treat them separately, and then I'm gonna go back and solve for it. So that does come up from time to time. I don't think you're gonna see it on these. Yeah. Yep. Yeah.
Just like a placeholder.
Exactly. It's some constant. So that's why usually you wait till you've kind of gotten the final solution, and then you go find what C is. Because if you try to find it with each one of these, it's going to keep changing, and you're just going to keep basically wasting time. Yeah. But there are things from time to time where, yes, those multiple C's do mean different things. Yeah. Or are useful. Okay. Yeah, and again, not to say that this solution isn't fine. There's nothing wrong with this. With this one, it's going to be easier to interpret. So oftentimes you solve for something and then they ask you a question later on about it. And while you can use this gets harder to interpret. Just kind of like, that's getting really hard for me to interpret. Yeah. Okay. Moving right along. Trying out this one. This one's barely a separation of variables, but I'll do it anyway. Just kind of show you, like, oh yeah. So you got dy dx, x squared. So, and I'm going to separate the variables. So I'm just going to multiply both sides by dx. So it's going to be dy is equal to x squared over 9 plus 7 over 9. And then this is dx. I got all these on Khan Academy, so not all of them are bangers. Integrate both sides. Integral of 1 with respect to y. Y. So next up, I can just treat these separately. So integral of x squared over 9 is just going to be x cubed over 9 times 3, which is just 27. Plus integral of a constant is just x, so 7 over 9 times x. And lastly, plus c. Oh, sorry, I should have said. Now, I could have written a plus c over here as well, but that's just going to go over here eventually. Convention that people do is you keep the plus c at the independent variable side, where y, you just don't write the plus c. So that's the combination of those c's. And I'm going to use that now from now on. I'm just going to make the plus c over there.
It's like pop goes on. Oh yeah. There we go.
Other questions? I hope this comes up on your guys' conversation.
Why do you hate me?
Oh, here we go now.
I can hear you. Yes, why do you hate me so much?
So, okay. So here we go again. This is, I think, the last one I'm gonna do. Last one I'm gonna do. You're glorified up here, and now you're.
Glorified on YouTube.
Yes.
When you
You're
subscribe to his channel.
subscribe to my channel. I'll send you royalties. So yeah. I can basically kind of cross multiply here, right? So it's going to be sine of y dy equals cosine of x dx.
I know, right? That's on beat.
And so we're going to integrate both sides. Integral of sine of y, negative cosine. So it's going to be negative cosine of y. We don't write the plus c for the dependent variable. And then for cosine,
Negative sign.
not negative sine, just sine. Yeah, plus c. And now here comes another fun one. So I got to isolate y. So how do I do that? Well, I'll multiply both sides by -1. So I got to multiply all that by -1. This negative cancels out with that negative. And then, so this will become negative sign here, but then that gets absorbed into the Uber constant. So we got cosine of y equals negative sine of x plus c. Because you can probably imagine, if I kept this minus c and I found out what the number, and I get a number, 4, that just means with the plus c, the number would be -4. Okay, yeah. So lastly, to undo the cosine of y, I want to take the inverse cosine, or arc cosine. And that'll give me y equals cosine of -1 of negative sine x plus c. And I don't think there's any properties that I can use with that. It's just that ugly thing that I got. Questions here before I go into velocity-dependent force problems? We're good? Okay. So now I'm going to do a problem that if you look at the thing, one of the handouts I gave you, it gives you step-by-step of what they did. So I'm going to do the same thing using my own way. They use limits of integration to solve. I always screw it up when I do it. And I don't know why. I don't know if it's like I get like, I don't know, something. I'm sure I can figure it out. Yeah. I feel more comfortable using the plus c with separation of variables. So what I do instead, so I'm going to use the plus c method. However, my method takes longer. So their method is shorter, but I get confused with some of those. I think it might just be because I'm doing 2 limits of integration at once. That kind of confused me, but yeah. Okay. The one, with the plus c, that's the one. Because again, if you want to reference the other one, it's on that piece of paper, and they show you the solution. I'm going to do my best too, because this actually came from 2013. Oh my God. I want to go to an actual AP exam question. And I want to kind of also point out how the points are distributed, because a lot of people sometimes, again, this is the heaviest calculus we've done, is this differential equation stuff. And a lot of people go like, oh God, that scares me. And they don't do a problem like this because of that, when you could still collect a lot of points even if you don't do that part. So you got a box of mass M. So box of mass M initially at rest, acted on by a constant applied force Fa, as shown in the figure above. The friction force between the block and the horizontal surface is assumed to be negligible. but the box and the drag force has a magnitude kV. So there is a drag force, but not a friction force. So it's air basically is doing this instead. You got Fa, box of mass m, where K, so V is the speed and K is a positive constant. Express all your answers in terms of the given quantities and fundamental constants as appropriate. Okay, so first, draw a free body diagram of the forces acting on the box. What forces will be acting on the box?
Gravity.
Gravity! Everybody's favorite. Mg. What else?
Normal force.
Normal force pointing up. In this case, it would cancel out the gravity. Doesn't always, though.
The applied force.
That applied force.
Okay, we did the drag.
Drag force, yeah. And now, typically, before we've had this, I've often drawn the drag force as being equal to, because when we've done drag forces in the past, it's always just been terminal velocity, at terminal velocity, because this would, because, right, basically, the box starts at rest, right? This applied force acts on it, it's going to speed up. But as it speeds up, let me write this a little bit bigger here. So I got a drag force here. And that's equal to, using this vector notation, it's equal to negative kV. So basically, and they're saying this is a positive constant. So V, whatever the direction that V is pointing, the force will point opposite the direction of the velocity. And again, I always think about riding my bike, right? The faster I go, the more wind blows in my face, right? And that means then the greater the drag force gets, right? So if I'm if I'm pushing myself at or the bike is pushing me at a constant force, eventually I'll go fast enough where I can't go any faster. I'll reach a terminal velocity, right, when I go. And that's what's happening here. Yeah. So, but yeah, and then again, in the past, we've kind of always said like, okay, now it just goes to the terminal velocity because we're going to get to now the calculus where we don't need to do that.
Is terminal velocity always different, like in certain situations, or is it always like the same?
Well, for example, it depends on a lot of things. So, but there's typically a constant, like, and that's the thing, drag force is quite messy. Because as you guys saw with the coffee filters, I think V squared was the best relationship, right? With the coffee filters. But like a lot of that kind of depends. So there's drag forces. The ones you guys are probably going to deal with the most are directly proportional to V or directly proportional to V squared. Those are the ones I've mostly seen. Every once in a while, yeah. But like drag force, I mean, this could be cubed. This could be 1/4. Like it could, and if you're an engineer, like that's what a lot of this is you kind of like fudging it, just try to fit the model as best as possible and then go with it, But for example, if you've probably seen people falling, skydiving, Janya, right? And you're skydiving when they're spread out, they're going really slow. But then they go, oh, I want to move faster down that way. Well, what do? I do this. So I've changed now my cross-sectional area. Now I can go faster downward when I do that. So by changing my cross-sectional area, my shape, I can increase my terminal velocity. So I'll go faster and I'll reach a new terminal velocity. If I want to slow down again, I can open my arms out and then I go back to, that old terminal velocity that I was at. Yeah. As the what? The skater, not necessarily the same thing, because with the skater, even if you were in empty space and you pulled yourself in, you would move faster. With this, if you were doing that in empty space, there's no drag force to hit against you. So you're using with the skater, there's no external force, net forces or torques that are doing anything. With the with this drag force thing, you're utilizing the drag force to change your terminal velocity. Yeah.
So the drag force depends a lot on like the shape or like area of the object.
Cross-sectional area is a big one. The fluid that you're moving through, and air is a fluid, right? So sometimes on the AP exam, they'll, instead of doing air, they'll do, you're moving through some liquid. You're moving through water. Or no, now you're moving through Jello. Like they can make up any kind of wacky fluid that they want to. Yeah.
What's the difference between like just area and then cross sectional?
Cross-sectional area. So because often we do it with like a like a wire. So if I have like a wire, right, the cross-sectional area of a wire is if I cut that wire, right, and I'm looking at just this part. You with me? So just this, that's the cross-sectional area of the wire. You cut it, and then you cut the wire, and then you look at that part of it, and it's just a circle now, right? So the cross-sectional area of this would be pi r squared. Yeah. And that's the thing, so if I had, like something falling like this, the cross-sectional area would be this circle, right? Because that's the thing that's pushing against the air, right? But if I dropped it like this, well, then the cross-sectional area would be, well, almost like a rectangle here, yeah. So, okay. Oh no, we're back. Am I still recording? Yes. Okay. So I do that. There we go. And if you do all this was out of 15 points. They gave you 1 point for the correct weight, 1 point for the correct normal force, 1 point for the correct applied force, and 1 point for the correct drag force. 4 points right there out of the 15 just for doing that. So please don't let this stuff scare you. So next up, B. It says, and this is a common phrase here, write but do not solve the differential equation that could be used to determine the speed, v, of the box as a function of time, t. You do not, if you need to draw anything other than what you've shown in part A to assist in your solution, use the space below. Do not add anything in the figure in part A. Yeah, because this is a common thing. A lot of times you might have to break something into its components. What they want you to do not draw those components on their dots. And the reason why is the grader is often just looking, they just want to see, oh, force, right direction, your good work. But if they see all of a sudden you have these components, they're like, are you considering that a force? What do you, and they don't want you to cause any confusion. Okay, but write but do not solve. I'll show you what that means. So I'm going to use Newton's second law. So here we go. F net equals ma. And then only in the x direction is it going to matter. So in the x direction, I've got the applied force pointing in the positive direction and kv pointing in the negative direction. So I'll say minus kv equals the mass times the acceleration. You could have done that last semester. I think it's 1 point for correct Newton law expression. So we're up to 5 points, or 1/3 there, and we haven't even done any differential equations. Oh, right, but do not solve the differential equation though. So here's that part: is you go, oh, v velocity, a acceleration. How does v relate to a? The integral or the derivative, right? V is the integral of acceleration, or a is the derivative of velocity. Yeah. So typically what we do with differential equations is we take the derivative form. There is something called an integral form as well. But we'll take the derivative form so we can replace a with what? First derivative of velocity with respect to time. And so once again, here I have an equation where the variable is equal to its own first derivative. And I can go, oh, this is a first order differential equation. This is what it means to write but not solve the differential equation. So literally, something you could have done last semester, to just changing this to dv dt. Not kidding, 1 point. 1 point, 1 point. So that's writing but not solving. And basically what you're doing, similar to when you write the d squared x over dt squared with the second order thing, you're telling the person reading this, I recognize this as a first order differential equation. You with me so far? Next step, separation of variables, because what they want is the velocity as a function. Well, sorry, that's not the next step. That was part B. So next step is, determine the magnitude of the velocity of the box. So we're not even there yet. The magnitude of the terminal velocity of the box. So with terminal velocity, do we remember what the acceleration is equal to? Zero, right? Terminal velocity is, let's go back here really quickly, right? Because remember, you got this applied force. There's no speed at first, right? There's no speed at first. And you got this applied force, and that applied force is going to cause you to accelerate, move faster. But then as you move faster, this now is going to start to increase. It went from 0 to something. Now it's going to start taking stuff away from here. So the applied force, the applied force is constant. It's going to start accelerating you. The second you start accelerating, the second you start moving, this now goes up. And that's going to take that out of that, which is going to decrease this. But the more this happens, the bigger this gets. But then the bigger this gets, this increases, and that's going to make this smaller. And eventually, this thing is going to catch up to it, and it's going to make it so when this equals this, it makes the acceleration 0. Again, if I go fast enough on my bike, I go fast, and I eventually reach terminal velocity, and I can't go any faster than that.
Will drag force ever be greater than applied force?
You can do that, I believe. I think that'd be like a situation where, remember when we said here, and then you go like that, and then you go back out like that. So doing this, I go faster, but if I go boom out like that, I think that's where the drag force is bigger than the applied force, because then I go to a lower, I think so. I haven't seen it much, though, in the physics problems, though, but yeah. Okay, so yes. So we're trying to find the terminal velocity, and the terminal velocity is when the acceleration is 0. So basically, then I can isolate for the terminal velocity. I get the terminal velocity is FA over K. You with me? Okay. Now we're getting to the differential equation part. Oh, and again, 1 point for that. So where are we at now? 4, 5, 6, 7. 7 points out of 15. Not bad. So next they say, use the differential equation from part B to derive an equation for the speed v of the box as a function of time t. Assume that at v equals 0 at time equals 0. So it's at rest when time equals 0. Okay. Here we go. First order differential equation. We're using separation of variables. I don't see any other t, so I can just multiply the dt over. And remember, it might seem tempting to just go, oh, plus kv. That won't work. So what we got to do is just divide this whole thing over. So let me start there. So I'm going to write dt over here, and then I'll write m, and then I got 1 over fa minus kv, and this is dv. You with me so far? Because the last thing I'm going to do, and this is just convention, you could totally integrate now, but convention is to kind of take the constants and throw them with the independent variable side. Typically because this side tends to be easier. So keep it with the constant. So I'm going to take the m and put it over there. And now I'm going to integrate both sides. The m is constant, so I'll just integrate here. And then here I'm going to integrate all this. I'll do the easy part first. 1 over m is constant. Integral of 1 with respect to time is just time. So it's going to be 1 over mt plus c. Again, I'm using the plus c method.
Sorry, what are they solving for
We're solving for the velocity. So basically, the goal here, just like the goal with the second order differential equations, is get the position as a function of time. Because once you got that, we call that an equation of motion. Once you have an equation of motion, you can take the derivative twice to get, you can take the derivative to get the velocity, and you can take the derivative to get the acceleration. And boom, now you know those things, and you can predict anything you want about that in that situation. Here, the goal is, well, using this, I can get the velocity as a function of time. That's the easiest thing to get. Because once I got the velocity as a function of time, I can take the derivative to get the well, I already got the acceleration, but I could take the integral to then get the position. All right? Yeah. And then boom, I got everything, and I can tell you whatever you want about this, how this is going to work. Okay. Next up then, okay, so it's I go, oh no. 1 over, and again, please be careful. This is a constant. This is a constant. This is a variable, right? So it's only t and v that are variables. K and fa are constants. And I go, oh, I don't know how to solve a problem like this. But wait, I see a function within a function. I can use u-substitution. Do we see where the function within the function is? No? All right. That. You got the function 1 over u. Well, this is my u. So I got u equals fa, a constant, minus kv. Next step, take the derivative of u with respect to v. Remember, v is the variable, so this is a constant. What's the derivative of a constant? 0. Yeah. Minus kv. Well, the derivative, again, k is a constant, but v, negative k. Again, process says next thing to do, isolate, in this case, dv. So it'll be du over negative k equals dv. And then I'm going to take all that and I'm going to plug it in there. This now becomes the integral of 1 over u, or I could just say, or no, 1 over u. And then this is du over negative k. And now I can solve this, right? That's a much easier integral to do than back there. So the negative k, though, I'll pull outside. You with me so far?
Yes.
Okay. What's the integral of 1 over u? Natural log of u. Nice. Yes. That's a tricky one. Every time, once you forget it, it shows up again. So, and a lot of solutions to differential equations are exponentials and logarithms. It just tends to be the case. And again, we don't add the plus c, but now I can replace the u with things that I know. So the u is going to be fa minus kv. And then, unfortunately, the v we have to isolate is embedded in an ln and multiplied by that. So it takes a little bit of algebra to get out of here. So I'm going to multiply both sides by negative k. The k would just get absorbed into the constant. So it's going to be negative k t over m, or negative k over mt plus c equals the natural log of, this will cancel with that. This will be fa minus kv. And then I got to undo the natural log. So I'm going to take the exponential of both sides. This cancels. And then I get e to the negative k over mt plus c. But remember, you can write that as multiplied by e to the c. That tends to be a better way to write this, which is all just absorbed into the uber c.
Is it negative k times t over m? Or negative k over m times t?
Both is fine.
Oh.
K times t over m is the same thing as k over m times t. Generally, I'm used to writing it this way because typically in physics, your independent variables here and you throw the constants in front of that thing. Yeah.
Oh, boy. Oh, this is like reminding me. That sounds like all the work I need to do.
Uh-oh.
Okay, I have to leave. Bye, good morning.
Peace out, dog.
Wait, careful, careful.
Oh.
Okay.
Oh, now we have to be careful.
I'm sorry.
What?
Wait.
So now it's not that bad. So I just need to isolate V. I like to add KV and then subtract this. I don't know why. This is the way I like to do it. So that's what I'll do. So I'll add KV. This is going to be KV equals, and then I'll subtract this term. Whoops, sorry. Let's simplify here. So it's going to be C e to the negative k over mt equals fa minus kv. So adding kv and then the ce term, so that's going to be kv equals fa minus ce to the negative k over mt. And then lastly, to isolate v, I'm going to divide everything by k. It's going to distribute there and there. So you get v, and typically we tend to then write the velocity as a function of time, is equal to fa over k minus, well, c divided by k is just going to be c. Once again, uber c strikes again. E to the negative k over mt. Oh, but we're not done. We're almost done. We're pretty much done. So, and I'll talk about the points as well in just a second. So next up, though, is this constant. So here's where I say, because I didn't use the limits of integration thing, I now have to find this constant. But it's not that bad. But you want to find out some data point. And we know that at time equals 0, how fast was it going? 0. So when time was 0, the velocity was equal to 0. So I can just write, well, 0 is equal to fa over k minus c e to the negative k over m times 0. Well, 0 times negative k over m is 0, and e to the 0 is 1. So basically then that leaves me with adding c to both sides. C is fa over k. And now I'm going to plug that in for my c, and that'll give me my last thing. So I got the velocity as a function of time is equal to fa over k minus fa over k e to the negative k over mt. Again, this is a solution. You are fine to just go like, yep, done, right? But we can kind of see here a prettier way to write this, because I got like terms, I could pull them out. So this becomes then the velocity as a function of time is equal to FA over K. And then in here is 1 minus e to the negative K over mt. And that's my answer. Yes. Okay. I know. No. We're going to go over points. Yeah. So where were we up to? 7 before we did this?
7 points.
I believe. Now, I think there's 4 points in all here. Let me make sure. I can't remember. You know what? I'll go grab it right here. Sorry. Just so I'm being accurate here. For demonstrating separation of variables. So if you tried to separate the variables, congratulations, 1 point. Now we're up to 8. So if I was like trying to separate the variables, there you go, 1 point there. For demonstrating the equation must be integrated.
Oh.
Second point. So now we're up to 9. Yeah. Next point. For demonstrating substitution using initial and final values or evaluating a constant of integration using bounding conditions. I did that back there. For this thing, they put in the limits of integration. They got the points there. I got the point later on. And then blah, blah, blah. So that's 3 points. Was there 1? Oh, attempting to solve for VT. So basically, once you integrate it, for going like, oh, now I got to isolate VT. So for trying to do that, another point. So sorry, there was 5 points total here. The 5th point, correct answer. Yes, exactly. So because I think, you can see there's a lot of algebra in this, right? To me, the hardest part is the algebra. Yeah. And it's so easy to get, messed up. And my calculus professor said, some things in calculus are easy. Algebra will always be hard. Yes. So, all right, there you go. And that's that. Those are those points. There is still some left. And I want to also say, because again, you could skip the differential equation part D and just go to part E, right? So you don't necessarily, in fact, I gave an exam question like this where you just kind of had to reason out what the graph would look like. And a lot of students were able to do it. So you don't necessarily need this to get this, but it does help. But a couple things really quickly, actually, before we get to the velocity as a function of time graph. First off, this equation should work because when time is 0, how fast is it going? 0. So when t is 0, this is e to the 0. E to the 0 equals 1. 1 minus 1 is 0. All that goes away. That works out. But then after a very long period of time, right, assuming, right, and my speed kept getting faster and faster and faster and faster, but eventually, what speed should I reach? The terminal velocity, right? So assuming this goes on forever, I'm not going to keep speeding up forever. I should reach some velocity and stay there, right? So what we can do, and I think both of you have gotten to limits, right?
I'm in pre-calculus.
Oh, no. Okay. All right. Never mind. Yep. Okay. So, well, it doesn't matter in physics. This is like really, you just basically kind of say it's really, really big. You don't have to say limits. But basically what I'm doing is a limit. So you go, okay, this is getting really, really, really big. So this is e to the negative of something really, really, really big, right? If we think about an exponential graph, y and x of y equals e to the negative x, it goes like this. Sorry, no, it doesn't. So as x gets really, really big, what does y become?
Really small.
Essentially what?
0.
Yes. So essentially, and this is a common question that they might ask. They say, okay, if time goes on for a long period of time, then this becomes 0. So we got 1 minus 0, that's 1. What does the velocity become? FA over K. which, if you recall, was the terminal velocity we calculated back here. I know, right? Like, and that's what's always nice too, is once you're done, you can then analyze it and go, does this match my intuition? And if it doesn't, maybe it's wrong. Or if it doesn't, maybe my thinking is wrong, right? Yeah. So there was an honor student just recently who was taking it, and they were like, I know this is wrong. This is incorrect. And I was like, write that down, because that means then at least that's incorrect. That's a good thing to know. Okay. You with me so far?
Yes.
So we know that the velocity starts at 0 and then is going to level out to some terminal velocity. Well, with that understanding, we can then do this last one, which is plot the velocity as a function of time. So we know it's going to start at 0. Plot velocity function of time, explicitly note any, and they say intercepts, asymptotes, maximum, minimum numerical values. So we essentially know it should level out. So the velocity should level out. So it's going to look something like that. Right? So it starts at 0 and then levels out. And where it levels out, that's the terminal velocity. But they want it in terms of things they gave us. So we're going to say FA over K. Yeah. Now, again, you should be able to reason this out. You did it back last semester of like, oh, the velocity, like, because also the acceleration should go to 0. So that means the slope should go to 0. But also, too, if you wanted to, you could graph that equation. Just give values to FA and K. Call it 1 and 2. Who cares? And then plug it in. You'll see you get a graph just like that. And again, when they say sketch, they mean, no numbers. Nothing, yeah.
And without knowing or doing D at all, like just giving up on that problem and just doing, I would be able to assume just looking at
Correct, right? Because again, we know that assuming you did then B and C right, you know that the acceleration goes to 0 once it reaches terminal velocity. So that must mean if I make a velocity versus time graph, the slope must end up at 0, right? And reaching that terminal velocity. So there's kind of only one way you could do that, making a continuous curve, because nature tends not to go, like that, right? It kind of curves in. So that's what that curve would look like, and then it would level off there. Because you also know you have to start it at 0. It's like that's the only way that curve could work. Other questions? You were right in that was going to take a while. All right. Bye.